This is a recording now of a presentation I made yesterday, September 30th, 2020, to the Society for Human Brain Mapping and Therapeutics. I'm the chair of the EEG and MEG track, and there will be a convention or get-together meeting in March 2021. But there's considerable interest in the relationship between magnetism and electricity in our subcommittee, as well as in many other places. So I was making this presentation of a previous work that I had done on the topic of MRI and EEG, and showing how they can be related. In fact, a transfer function can be developed so that if one knows the certain features of the MRI, the quantitative MRI, then one can predict the EEG. And if one has quantitative EEG, one can predict the MRI. And actually, you can actually take an MRI slice and change the pixel intensity depending upon the EEG, and literally you can derive an MRI image without actually measuring the MRI. In any case, the process, and I'm going to just begin this by expanding this screen and give a bit of a history, which begins with the National Institutes of Health, where I was a project manager for the first 128 channel EEG system at the National Institutes of Health at the Human Brain Mapping Program, the first decade of the Human Brain Mapping Initiative. Over $2 billion was put into that program. And I was part of the team to do multimodal registration of different imaging modalities. PET scans could be co-registered with structural MRI and EEG, MEG, SPECT scans. Later, near the end of the decade, the functional MRI came into being. It's not as accurate as PET scans, and in a minute I'll be showing you how we could co-register the PET with the EEG and MRI. And one experiment that we did, among many, was a voluntary thumb movement, which produces an event-related potential, or evoked potential, in which there is a sensor on the subject's thumb to detect precisely when in time the thumb moves. The subjects are asked to voluntarily move their thumb when they feel like it. So that may happen every 3 seconds or 5 or 7 seconds. Whenever somebody has the urge to move their thumb, then they will move it. That gives us a time point at 0.0, where the vertical line is on the right. And then we can go back in time and look at the data points in the EEG that preceded the thumb movement, as well as the events in the brain that happened just after the movement. During this actually, when you do move your thumb, you produce what's called a motor potential. And you can then average that potential like you would an evoked potential based upon the onset of the thumb movement. And then from that, you can compute inverse solutions as to the sources of the event-related potential. In this case, we came up with 3 dipoles that accounted for over 95% of the variance in the event-related potential. And we used the Scherg discrete inverse solution. We had 32-channel EEG for this particular experiment. And you can see on the left where the dipoles are located. Dipoles 1 and 2 are in the left and right hemispheres in the sensory motor cortex, and dipole 3 is in the supplemental motor cortex, and also very close to the anterior cingulate gyrus. And you can see the time course of these three different dipoles at about 212 milliseconds before the onset of the movement. That is when the individual had conscious intent to move their thumb. And then you can see the evoked potential build up. And then once the movement occurs, there's just before the movement, actually, you can see that in dipole 2, there is a sudden output of action potentials in the pyramidal tract through the motor system, down through the brainstem. Decussation of the pyramidal tract then goes to the opposite side of the spinal cord. So you then goes to activate the movement of the thumb. Then once the thumb moves, there's then kinesthetic feedback that comes to the sensory cortex, and you can see that in dipole 1. And there's a mismatch that is going on as to the correctness of the movement, or whether errors occur. Then that feedback process dynamically goes on all the time when we move. If you have the intent to move, there will be the action of movement, and then there will be feedback as to the success or failure of that movement. And the process then refines the quality of our movement. It's very important, and it spontaneously happens, and you can see it can happen within 150 milliseconds, 200 milliseconds. And the whole process is quick. This is the co-registration of the PET scanner in the same subject who is doing the same exact task in the PET scanner, not at the same moment of time, but we simply did the task 2 times, once in the PET scanner and once with EEG electrodes on. And the dipole in the supplemental motor cortex is shown here. It co-registered within about 4 or 5 millimeters. Typically, it's difficult to get accuracy of less than 1 centimeter, but nonetheless, we came very close. And dipoles 1 and 2 also were fairly close to the activated PET. Now, what the PET scan is the oxygenated blood has been radioactively labeled, or it has positrons in it. Actually, you irradiate it in a cyclotron, and then it's injected into subjects, or there's other ways people can ingest, but in this case it's injected. And those parts of the brain that become active, there's dilation of the arteries to those neurons that are active, and the oxygenated blood then flows to that part of the brain to support the neural activity. That's PET scans. Now, functional MRI is with deoxygenated blood. So once it's the blood oxygen is utilized for metabolism and the ATP transfer of energy transfer, then the deoxygenated blood actually travels some distance away. It's like a tributary of a river into little small paths. And so functional MRI has a weaker signal, and it's often at quite a distance away from the areas that actually get active. It's part of the reason why there's much more error in the literature in functional MRI, because of the noise, and also because of the statistical methods were used. That's recent papers are coming out showing the error in functional MRI. Now, one thing you can do also that we did is calculate the instantaneous coherence. And coherence is the functional connectivity. In general, the analogy that we use is that imagine a sports stadium and a parking lot with a road connecting the sports stadium to the parking lot. That's structural MRI. Then imagine cars fill up the parking lot with people who are going to attend the football game, and then a little while later, the sports stadium fills up. And then also it's true that when people leave the sports stadium, then a little while later, the cars leave the parking lot. That's functional connectivity. It's a correlation. It's a cross correlation. and measures like coherence, lag coherence, instantaneous coherence, cross correlations, covariance analyses. Those are all in that category of functional neural imaging and functional connectivity. Effective connectivity is where you count the number of people that travel from the parking lot to the sports stadium, and you count the number of people that go from the sports stadium to the parking lot. That's a measure of both the magnitude and direction of information flow. So that's effective connectivity. But of course, they're dependent upon the parking lot, the street, and the sports stadium. The underlying structure is actually fundamental. So all three of these types of connectivity, structural, effective, and functional, are very important. Now, one thing to note that the structural connectivity is basically there whether you're alive or you're dead. And certainly if you're right after death, you'll see that the MRI does not change in its basic structure. But certainly or if there's severe mental, like a coma and things like this, or even sleep, large state changes, then the effective connectivity is going to be changing quite a bit. But what I'm going to be showing you is that there are very subtle relationships between the EEG and the structure itself. Now, this is just another example of the instantaneous coherence on the y-axis and the motor movement dynamic on the x-axis at time. The negative numbers are the period of time before the thumb moved. And what's going on here, this is a switching dynamic in which the supplemental motor area will inhibit the contralateral or the ipsilateral side. So if you move your right thumb, your left motor cortex is actually activating that. But they're in competition, and you can see the switching between the two, and the magnitude of the coupling is higher with the ipsilateral motor cortex, because this individual is a right-handed subject, and it's low connectivity from the other cortex, but then they switch shortly after. That was in 1993, 94. I left the National Institutes of Health and got a position at the Bay Pines VA Medical Center. And also I was an adjunct professor in the Department of Radiology and Neurology at the University of South Florida. And I was in charge of the coordination of EEG, MRIs, and neuropsych tests in traumatically brain injured individuals from 4 different VA hospitals and 3 military bases. And so this was fairly early along in this program where we were measuring the MRI of normal subjects, then mild, moderate, and severe TBI. We were also at this time working with Alzheimer's patients. And I could see, as we looked at the distribution of the gray and the white matter in the MRIs and did analyses on them, you can see that there were the more severe the Alzheimer's, then the less distinct was gray matter and white matter in the MRI. And the same turned out to be true of TBI subjects. So I became interested in quantifying the integrity and the separability, the differentiation of tissues in the brain as a function of injury. And this is the abstract of that. This paper can be downloaded from our website. Then to the society, I've given them the access to the URL, so people have already downloaded it. And if they haven't, I recommend that you do. This is just a representative example of one of the slices. This happened to be a 1.5 Tesla MRI machine. We also have 3 Tesla MRIs in some of these studies. But we had various landmarks so we could identify different aspects of the MRI. And we segmented the MRI into gray matter, white matter, and cerebrospinal fluid. And then we looked at the distribution of the pixel intensity for different subjects. Now, the 2 columns to the left are the gray and white matter using T2 relaxation time and 2 normal subjects. The and there's 1, 2, 3, 10 slices. So the rows are slices going from deep in the brain at the bottom to the top of the cortex at the top. And the 2 columns on the right are 10 slices from 2 TBI patients. And what you can see is that the normal subjects, there's very clear, the first peak to the left is the white matter, and the peak to the right is gray matter. And the reason why they're different in an MRI is because there's different amounts of water or protons. The water protons are what the MRI is looking at. And the reason there's different amounts of water is partly because the white matter has myelin, which is a fat molecule, and it expels water. Okay, so there's less water in the white matter. In the gray matter, there is no myelin, and there's more water. And so that difference between the 2 peaks that you see there is the gray and the white matter proton density, or and it's not. We looked at T1 proton density and T2. I'm pretty sure this is T2, but they're related to each other. Proton density is one of the components is used to calculate what's called the Bloch equation, and I'll show this later. But remarkably, the TBI patient is as a single curve. It's a uniform distribution, and there's very little differentiation between gray and white matter. And this was true of all of the subjects, and I'll show you what we found in a minute. Now, what we calculated and tried to come up with quantitative measures of the degree of tissue separation. And we did it in a couple ways. On the left side, the A figure is the actual pixel intensity from a normal subject. And the B is I calculated the first derivative of that distribution. So you can see that there's a positive first derivative, and then there's a negative first derivative at the valley between the 2 peaks, and then there's another positive peak in the first derivative for the second peak. And that's quite different than what you see in C and D. C is from a TBI patient, and D is the first derivative. That first derivative of the uniform distribution is positive as it goes up, and then negative as the sign of the derivative changes, and it declines. But it does not have 2 positive peaks. So we can measure the magnitude of the positive first derivative and second derivative, the presence or absence of it, the timing of it, or the distribution and separation. Those became quantitative measures. In addition, we calculated just skewness and kurtosis of these distributions. There's another way to quantify the distribution of the pixel intensity in an MRI slice. We compared, in the top is the first derivative of the normals, or the dark squares, and the dashed lines on the bottom is a TBI patient. And you can see there's quite a bit of difference in the first derivative, and it's different at different slices. The bottom one is skewness and of TBI, it's the amount of peakedness, and you can see that's also significantly different, but it's not, slices 4 and 5 and 6 are much more significant than slices 1 and 2 or 8 and 9. So it's not all the slices. This is a picture of what we did is we identified the pixels that are intermediate between gray and white matter, and we colored them yellow. Now, normal subjects have some pixels between gray and white matter. With a 1.5 Tesla magnet with 3 Tesla, there's fewer intermediate. There's more differentiation that you can see. And now there's 7 Tesla MRIs. I would imagine you can find really micro tissue boundaries using statistics like this to quantify pathologies in greater detail than we can here. And here you can see that the mild TBI had more yellow pixels, and then the moderate more, and then the severe even more. And it allowed us to also just look at the distributions of these different tissue compartments In normals, you can see a very clear difference between a muscle and white matter, gray matter, and cerebral spinal fluid. Those are 3 normal subjects on the left column. And the right are 3 TBI patients where there's much less separation. There's a lot more overlap between them. And we compared T1 to proton density to T2. And we found that the T2 was more significantly different between normal and TBIs. For those that are not real familiar with MRI terminology, T2 is it's called the transverse relaxation time. The way to imagine that is imagine a top that's spinning, and actually all your water protons are doing this. But when you put your head in the magnet, then all these little tops line up with the magnetic field. So they're all spinning together inside the magnet. The greater the strength of the magnet, then the higher the frequency of the spin. Faster they spin, it's called the Lamar frequency. And so while the person's in the MRI and all the protons are spinning, your head is actually in a chamber around your head, in which there's wires going around in that little compartment that you have your head in. And then the radio pulses are presented. Now the radio pulses will knock these tops down at right angles. So imagine that they're upright vertically, and now they become horizontal, but they're still spinning, but now they're spinning in the plane of the flat plane, the 90-degree shift. And that's a signal that's then detected in the MRI machine. But these tops then slowly come back up to where they were before the pulse knocked them down. If you put a glass of water in the MRI scanner, it takes about 3 or 4 seconds for the water to come back up, the protons to come back up to their original orientation when they're spinning. If you put some metal or more dense material in, then the T2 relaxation time is in microseconds. So it depends on the concentration of the water and the amount of macromolecules in a space that determines how fast the protons return to their original position before they got knocked down. Now, proton density is measuring actually the number of protons. And so I wanted to know, well, what's going on here? And so we calculated we solved what's called the Bloch equation to calculate the length of time it takes for T2 relaxation time to occur. And this is a patient, this happened to be, I think it's a 3 Tesla, 15 slices. And this is how we calculated we solved the Bloch equations. Bloch got a Nobel Prize actually, in, I think 1953 or so, for determining this calculation. And it's taking the difference between the proton density and the echo time for T2 and divided by the ratio, a log of the ratio of the two in the denominator. And that's how you calculate it. The number comes out in milliseconds. And then we could look at the gray and white matter and color them depending upon the time. And the distribution of the white matter, you can see in the lower left that it's roughly 55 milliseconds to 80 milliseconds for relaxation time, whereas gray matter is roughly 60 milliseconds out to 140 milliseconds, because there's more water in the gray matter than the white matter. And the location of the relaxation time of the protons is, you can see in the upper part, it can be colored with different colors. The red is the longer relaxation times, yellow, etc. The blue is the faster ones, or shorter ones. And then we looked at the different relaxation times and correlated T2 relaxation time with EEG amplitude for delta, theta, alpha, and beta. And we found that the longer the T2 relaxation time, then the more delta, and the shorter the T2 relaxation time, the more beta. and they're inversely related. And we could see this graphically, like in examples like this from different patients, groups of subjects. And again, you see that as the T2 relaxation time lengthens, then beta goes down. As T2 relaxation time lengthens, then delta goes up. And what that indicates is that the integrity of the protein lipid molecules have been compromised from the patients with TBI from mild, moderate to severe compared to normals. Essentially, the tissues of the brain, the macromolecules, are separating different spaces in the brain. In the case of neurons, there's ionic channels opening and closing for sodium and potassium, chlorine, etc., that determine the electrical activity of the neurons, synaptic activity as well as action potentials. And so the integrity of the protein lipid molecules are very, very important in the functioning of the brain, and that's what gives the MRI its structure. It's the separation of these protein lipid molecules and the organization of them that we're looking at. We also then correlated T2 relaxation time with neuropsychological tests. In this case, it's the digit span forward, digit span backwards, Boston naming, California verbal learning test. There's a number of neuropsych tests, and we found the same. Well, what essentially we found that the longer the T2 relaxation time, then the worse subjects did on these neuropsychological exams. And the more severe the TBI, then the longer the T2 relaxation time. So they're all going together. So this is a measure of showing that the underlying problem of in the patients with their clinical symptoms is related to the integrity of the protein lipid molecules, which is reflected in the EEG as well as in the neuropsych test. So this is digit span and California verbal learning, etc., as it relates to the beta frequency band and neuropsychs. And so we summarized the various statistics. They're all fairly significant. Alpha was not as significant, but delta and beta were. Alpha and theta were not as significant in some tests. In verbal learning, they were important. All of them were. And so we just characterized the severity of closed head injuries, showing you get an increased delta and reduced beta as a function of the severity of the trauma, and that's reflected also in the integrity of the protein lipid molecules inside their brains as quantified by the MRI. Now, this is quantitative MRI. It's very difficult to see this if you just visually examine the MRI slices. You need to quantify it. This is just the same thing that may help some to understand what T1, T2, and proton density is. I recommend that you probably read the paper to get more detail on that. The white matter has myelin, so it's expelling, it's hydrophobic water molecules, whereas the gray matter does not. So that's why there's differences between the gray and the white matter in the MRI. And the circuitry in C is where there's local inhibitory loops in the gray matter with no myelin, but the pyramidal neurons send axons out into the white matter that travel long distances. And as a consequence, there's two compartments. There's a local compartment, which is made up of the inhibitory loops and local domains. The faster those loops go, the higher the frequency of the EEG. That's a short distance compartment. And then there's a long distance compartment where the frontal lobes talk to the parietal lobes, for example, or the occipital lobes talk to the frontal lobes. Locally, you have the local compartment where the neurons get active, but then they send action potentials out through the white matter to then influence the activity in clusters of neurons some distance away. That's also important. So we wanted to know what's the relationship between T2 relaxation time and the MRI and functional connectivity. You know, the people leaving the stadium and then the cars depart from the parking lot and vice versa. So we wanted to study this. And we did the same computation of the block equations. But we calculated coherence at different distances in different directions. We went from the back of the head forward and the front of the head back. It's anterior to posterior, posterior to anterior. And for example, posterior to anterior, O1 P3 is roughly 7 centimeters. O1 C3 is 14 centimeters. O1 F3 is 21 centimeters. O1 FP1 is 28 centimeters. So, and because coherence is related to it, and phase differences, and we also did this with phase differences, varies as a function of physiological parameters, including the distance between the electrodes, because it takes time to go from point A to point B. So the conduction velocity is an important part of the coherence. And you can see that coherence does decrease as a function of distance. We showed, actually Paul Nunez was the first to actually show it in 1981 in his book on the neurophysics of the EEG, in which there's two compartments. You can see the compartments anatomically, but in terms of the EEG, that was really pointed out by Paul Nunez, the first that I know of. And I then replicated that when I was at the University of Maryland in 1986 with a very large group of subjects, and we studied it in more detail. And what you can see is that the local compartment, it has a property we described it as dispersion. It just the density of connections in the local domain decreases as a function of distance to any other neighbors. It drops off exponentially. At the same time, the axons go out into the long distance compartment, and that decreases, the density of connections decreases as a function of distance, also, I mean, just generally, but it will increase when there's termination somewhere, let's say occipital lobes and frontal lobes. You'll see an increase in coherence at this long distance because the frontal and occipital are very important connected. So it's a U-shaped type of relationship of coherence as a function of distance. It's not just a simple drop off with distance. It will increase if there's two clusters of neurons at some distance away are talking to each other. Frontal parietal is another example. But it's different if you go to anterior to posterior, posterior anterior. That's because there's different amounts of packing density in the different parts of the brain. Now, for example, the posterior parts of the brain have much higher packing density of the neurons. There's more neurons per unit area as compared to the frontal lobes. Frontal lobes have larger dendrites. Neurons are farther apart, and so the neurons are not as tightly packed. So what we found was that the longer the T2 relaxation time, then coherence would go up, and so then that's largely because that's in the long distance. In the short distance, the longer the T2 relaxation time, the coherence would go down. And because of the integrity, because coherence is a function of the number of connections and the synaptic drives. So the strength of the synapses and the number of the connections determine the magnitude of the coherence. So with reduced connectivity, reduced integrity of protein lipid molecules, there's a distortion of the connectivity as a function of space as measured by coherence. And we saw this in a lot of different ways. One is, if you look at alpha, you'll see the two compartments is very clear. The 7 and 14 centimeters are one set of coherence values, and then it jumps up to at 21 and 28 centimeters. There's other examples of these two compartments. Another example of the two compartments. And so the two-compartmental model of coherence, which this actually comes straight from our 1986 publication, can be characterized in this way, where are these local interactions where the density of connections decreases as a function of distance in the short distance domain, short compartment. Like if you get a pen, a felt pen, and put it on a sponge, you'll see the water just, the color of the red pen, let's say, will just disperse, diffuse out. It's that kind of physics that you can see it, just to characterize it mathematically. It doesn't actually work that way, but it's a visualization. As opposed to the long distance compartment, where there's a feedback loop. So the occipital lobes talk to the frontal lobes, and there's fairly large, the frontal occipital fasciculus is quite a large fasciculus, and so there's an increase in coherence, and then it's a two-way street as it goes back. And so we characterize the normal subjects will have long distance coherence that is smaller, lower than short distance coherence. But the severe TBI, there's a reduction in coherence in both compartments as a function of the severity of the TBI. So we wanted to go deeper into this. What can we relate at a biophysical level and more clearly the relationship between T2 relaxation time and the EEG power spectrum? And we again calculated the block equation. You can see on the left. On the right is the Laplacian operator that's used in physics. It's looking at the complexity of the space. There's an X, Y, and Z coordinate, and there's the second spatial derivative, so that the more complicated and heterogeneous the MRI is, then the larger the del square. This is also related to dispersion. So I calculated the spatial second derivative to get a measure of the complexity of the physical space, the actual complexity of the MRI space inside the subject's brain. So it's quantitative. And then we compared just the T2 relaxation time on the left, and we also looked at the spatial Laplacian, which you can see on the right, as a function of T2 relaxation time. And we looked at current density. We also looked at electrical potentials. They were similar. So when neurons get active, they generate current at right angles to the skull, and the electrical field is more widely distributed. So we wanted to compare the two. They're all related and correlate well. The relationship between T2 relaxation time and the alpha EEG is what we saw previously. You can see it decreases as a function of the amount of water and the less integrity of the protein lipid molecules. And if we measure the spatial Laplacian, what we see is that the more complicated and heterogeneous the environment, the spatial environment itself, then the higher is alpha. So alpha is related to the differentiation of tissue spaces. A healthy brain has got plenty of differentiation of tissue spaces. With traumatic brain injury and Alzheimer's, there's a breakdown of the integrity of the tissues. There's more water flowing, and there's less complexity in the brain structurally. It's related to entropy too, but we just talked about pronounced spatial complexity. And then we compared the Laplacian to the electrical potential. Electrical potentials at the top. This is the alpha band, and you can see which electrodes are related to which slices. So slice 1, there was no significant relationship. We saw that earlier. The top slices and the bottom slices. The middle slices had much more relationship. And that's largely because of the relationship of the brain to the skull, which is more in the middle slices. And there's more fibers there that are stretched and damaged by the percussion forces and the contusion forces and other forces that are imparted to the skull when somebody has a traumatic brain injury. And then we correlated the T2 relaxation time and the spatial Laplacian with the neuropsych measures, found that many of them are highly significant. This is an example for WACE-R vocabulary test on the upper left with T2 relaxation time. The longer the T2 relaxation time, then the lower the scores are in the neuropsych test. And then the spatial Laplacian shows the opposite. That is, the more complicated the brain, the and the more differentiated it is in space, structurally, then the higher the scores are, the more intelligent. The IQ scores are higher. The various word fluency tests, digit span, etc., all showed this kind of relationship. And then we summarized that in these tables. And then we also looked at EEG with respect to the Laplacian and with power and current density. So we did both. And I'm not going to spend a lot of time on this, but this shows the differences between the Laplacian and the T2, highly significant differences between TBIs and normals at a variety of different frequencies, especially with the T2 Laplacian with the spatial complexity metric. So we summarized this, tried to theorize, well, what's going on here? This helps illustrate it. We have electrodes at the surface, and then underneath is these domains of neurons. There's clusters of neurons. Each little cube may be several million neurons that synchronize, and they contribute to the electrical potential at the scalp surface. But you can characterize each of these little volumes in the lower left using what's called the Poisson equation, where conductivity is the sigma symbol, del square is the operator, the mathematical operator, and then phi is the electrical potential, is proportional to 1 over T2 relaxation time. So we can model that. That actually is how the data was coming out. If you looked at the current density and electrical potential, that explains why there's an inverse relationship between the length of T2 relaxation time and the electrical potential. You can also characterize it as an equivalent circuit where there's conductance and inductance and capacitance, and where activity is flowing or moving around from pyramidal neurons through the white matter up to the another location, frontal temporal, frontal parietal, etc., going back and forth. These are circuits. Actually, they're loops in the brain. And so you can characterize what's going on here by modeling it this way, which is consistent with all of the neurophysiology. This is Walter Freeman, Paul Nunez. This is the way the brain is wired. And this allowed us then to create a transfer function. The equation to the transfer function is shown at the top there, in which we could relate the MRI T2 relaxation time to the scalp EEG spectrum with synaptic synchronization onto the dendrites and cell bodies. But this allows us also to reverse this transfer function. That is, if you know the MRI, you can predict the EEG spectrum. And that's really what we're showing here. The MRIs, you can see those curves. This is in the alpha frequency band. We looked at it at different frequencies, but we didn't have a lot of space. We want to just show it for this one. And where T2 changes from 68 milliseconds to 86 milliseconds. But as T2 lengthens, then the amplitude of the alpha peak decreases and delta increases, just like we saw in our paper. So we developed this transfer function that allows one to link the current density produced by the brain and the electrical potential of the EEG to the molecular integrity of the protein lipid molecules of various membranes and tissue spaces inside the brain. And we then called this magnetic electroencephalography, MRE, and later on, there is the appendix that does go into some of this math, because you can characterize it very succinctly. So I took just the regular standard vector calculus developed by Poisson and Laplace, and later Green's function, which was two-dimensional, and then Stokes took Green's function and spun it around. It became 3 dimensions, and he developed other parts of vector calculus, and it actually developed what's called curl. So the top one there is divergence, then there's gradient, and then there's curl. And Maxwell's equations used all of 3 of these parts of vector calculus. But you can summarize both the MRI and the EEG using the same, essentially Maxwell's equations, with different, the form of the mathematics is the same in terms of this divergence and curl and gradient. And so electricity and the EEG and the structural integrity of the MRI can be formally linked using simple, the regular calculus that everybody learns if you take college physics. And here are the publications. All of these publications I mentioned are available on our website at www.appliedneuroscience.com. Go to articles and you'll find these publications there, so you can study them at your leisure. And then just to bring us up to date, that all of this took place in 1989, a lot of that, 87, 89, and then 2001. In 2001, George Bush became president, and we learned from Dr. Salazar, he was the head of the program, because this is a large TBI program, that the priorities have been shifted, that the new Congress is coming in, and we thought that our budget would be cut, so we flew to Washington. We met at a small subcommittee of the House of Representatives, and it's about 6 or 7 of us, and we all gave our talk and showed what we were doing, and I showed this stuff with MRI, and there's so many people with traumatic brain injury in all these places, veterans and active duty military, and they listened politely, and at the end they said, well, do you know anything about prostate cancer? And we looked dumbfounded. We looked at each other and asked me, Dr. Thatcher, do you know anything about prostate cancer? I said, no, unfortunately, I don't. And that's all they were interested in. They said, okay, thank you. And we left. Hardly any comment from them. But we knew that this program is going to be terminated. And sure enough, a few months later, I think it was in June of 2001, it's before 9/11, it was terminated and the money went to prostate cancer. A lot of it. Some of the program remained, but about 80% of it was terminated. And so I moved on and created the company called Applied Neuroscience. I was going to just put my resume out and work as a professor, but because I had 20,000 subjects in my database, I've been doing this for quite a while, I thought it had potential commercially to help evaluate traumatic brain injury and Alzheimer's and autism and learning disabilities and all kinds of things. And so here's where we are today. This is it's a real-time three-dimensional inverse solution. This is a distributed inverse solution. It's called SW Loretta. In 1994, distributed solutions were actually they came about in the 1970s, 1980s. But Roberto Pascual Marquis used one of the methods referred to as Loretta. That's low resolution electromagnetic tomography. And there's several others. I review these all in my handbook of quantitative EEG and EEG biofeedback that one also can look at. And we implemented the math then in 2014, 15. Been working on this for about 3 years. This is the Neuronavigator. SW Loretta has 12,700 voxels approximately. You can navigate throughout this system. These are a particular network. I think it's the attention network. The three-dimensional hubs are seen, which are Brodmann areas. That the second decade, by the way, actually we saw Brodmann areas were resurrected in the first decade of the human brain mapping program. There's huge consistency for all the Brodmann areas, both for EEG, MEG, and PET scan and SPECT scan in the 1990s. And it's now become the standard. So there's now an atlas to coordinate and co-register. They call it Telluric Atlas and the Montreal Neurological Atlas, which are linear transforms of each other. So if you know one, you know the other. And now the picture on the right is called the connectome. That's a two-dimensional image of the three-dimensional networks you see in the middle. And that's where the second $2 billion went for the second decade, along with other expansions into functional MRI and diffusion tensor imaging. And so that's where we are today. We're continuing what was accomplished by linking the structure of the MRI and T2 relaxation time with the EEG was greater credibility for EEG, a greater foundation, so you can better understand what EEG is, why it changes if there's somebody who has a traumatic brain injury or a degenerative disorder such as Alzheimer's. There is a physical relationship between the underlying sources of the EEG and the EEG itself. And that's another reason why not to use improper methods such as independent components analysis to replace the EEG with a digital time series that allegedly removes artifact, which actually just spreads it out, because now the EEG is no longer related to the underlying physiology. If we had done ICA, independent components analysis, replacement of the EEG, we would probably have not seen any relationship between T2 relaxation time and the various frequencies of the EEG. And certainly not with the coherence. Maybe we would with the frequencies because it's not with the amplitude, because it doesn't distort the amplitude too much, depending on how you do it, but it certainly distorts all of the coherence and the connectivities. So luckily, that particular method was not prominent then, and it's not prominent now, but it is growing, and will disallow people to connect the EEG to the underlying physiology or the brain of the subject themselves. It's just another example of what we can do today by building upon the science that we developed before. These are networks as developed by functional MRI, largely by PET scans and functional MRI. We just simply take the known networks related to different symptoms: attention network, anxiety network, addiction network, memory network, default network, etc., from the scientific literature, and then use the inverse solution. It's called SW Loretta. It's standardized weighted Loretta. It gives you depth, including the cerebellum, that just S Loretta itself does not. For example, here you can see this is diffusion tensor imaging. We can color the diffusion tensor imaging fibers according to the magnitude of the coupling, both in the raw scores and z-scores. And then here's the cerebellum, the deeper parts of the cerebellum, the vermis, the subthalamus, the red nucleus, the thalamus, and then the sensory motor cortex at the top, and the magnitude of these, the lines connecting the hubs, these are Brodmann areas and regions of interest, are the magnitude of coherence, or phase differences, or the information flow, etc. All the metrics of both effective connectivity, functional connectivity, and structural connectivity now are integrated in this program. It's called NeuroNavigator inside of NeuroGuide. So with that was what I presented, and hopefully this is informative and useful for people. And you're welcome to give me an email or contact our people at appliedneuroscience.com at any time you wish. So take care.